Welcome back, everyone, to another episode. This episode, we have Adrien, who is from the University of Liège. Adrien will be talking to us about the myth of exploration in policy gradients, such an intriguing title. So, Adrien, we're very excited to have you with us. The floor is yours, and please start. Go ahead.
Yes, thank you for the invitation. So indeed, the title sounds a bit intriguing. And what we're going to discuss is the influence of adding intrinsic reward bonuses when you do a policy gradient algorithm. So to start a bit with an introduction, I guess you have seen this figure 1,000 times, but reinforcement learning is about making decision when you have an environment in which you can apply actions that will make evolve a state and provide reward through the evolution of the state. And we call the ARL agent the thing that is going to take this action depending on the observation of the state that's gathering through time. So one interesting thing about ARL is that it requires an oracle model, so meaning that you have to be able to sample from something or to have a data set that you have built at some point. And even though the optimization may take a lot of time, in fact, the execution may be fast because you have your policy that is some one-to-one mapping from the state to the actions. So some quick notations, we will call S the state space, A the action space, P0 and P for the transition and the initial distribution of the Markov chain that is built, and rho is the reward function. And we are looking at Markov stochastic policies, so policies that take as input a state, the current state, in fact, of the system, and provide a distribution over the action space. And for the sake of simplicity, we will only look at continuous cases, so we will work on the density of the policy, of the distribution over the actions. And so in policy gradient or in direct policy optimization, direct policy search, what we try to maximize is the infinite discounted sum of rewards that you observe. So we generate trajectories from state 0 as 0 to the infinity, and we want to maximize the discounted sum of rewards, which we can write as the expectation of the reward function on expectation over this distribution, which is called the occupancy, the state occupancy measure, which represents basically some kind of average of state that is going to be visited through time. And note that there is already a first typo here. There is a factor 1 over 1 minus gamma that is missing. And so in policy gradients, what we do is we parameterize the policy with typically a neural network, and we perform stochastic gradient ascent on this objective function. So there is one typical observation when we do policy gradient is that if we want the algorithm to converge, the policies shall remain sufficiently stochastic during the optimization procedure. So typically, if at some point the distribution of actions over the actions evolves towards something that is a Dirac over one action, well, it may stop working. And so what we see is that in several optimization procedure, if we simply maximize this previous objective, what may happen is that it converges towards something that is locally optimum because it has become too deterministic to explore, as it is usually called. But we are going to see that basically it's more like an artifact of the optimization function that you work on. And so in order to... Yes, come again, sorry.
So, so this is interesting what you say. So you're saying that as we optimize, the policy becomes more deterministic, right?
Yes, this is not theoretical stuff. It's more of an observation. And so typically, so the intuition behind that is that usually if you are at some bad point in your policy space, well, and you have a lot of variance, well, reducing the variance usually will improve the performance of the policy. So typically, if you're doing very bad actions, it's better to do something that is less bad more often. And so this can happen by reducing the the stochasticity of the policy, so the variance when it's parameterized by a neural network. And so
Okay,
at the end of the day, you end up with something that is very deterministic and that is in a kind of local optimum.
I see. Okay. And in terms of what you just said about the intuition, would this also hold if I have sparse reward setup? Because how do I know that kind of locally my action is bad, if I just get zero reward most of the time?
Well, this is a good question. So we are going, in fact, to cover the sparse rewards problem a bit later. And what we may see is that there are two things to distinguish, which are the local optimum in terms of the objective function itself, and then the fictive local optimum, if I may call them like that, just that result from having a bad estimate of the gradient. So when you perform Monte Carlo estimation for getting an estimate, you may have something that is usually zero. That's because it's a sparse reward problem. And so it may indicate that you are in a local optimum or that at a saddle point, or basically you have a zero gradient, but it's a statistical problem. It's not a real estimate. And so we are going to distinguish these two effects.
Okay, cool, thanks.
And so in practice, in the policy gradients, in order to keep the policy sufficiently stochastic, in order to implement these exploration stuff, what we do is to optimize the surrogate objective. And so this surrogate may look like that. So you have basically this expectation. So here the factor is not missing anymore. And so you optimize basically the expectation of the reward function. So it's the same plus, so k intrinsic reward bonuses. So basically k additional reward bonuses that are designed in order to increase the stochasticity of the policy. And so how are these reward bonuses, so the intrinsic reward exploration bonuses selected? Well, there are two classes of reward bonuses. The first is to have a model that will basically provide you some kind of uncertainty over the model. So basically, if you have, for example, a neural network that you have trained for predicting the next state, well, what you can do is to have during the optimization, penalize basically if you are going to have a bad prediction. And so what you are going to do is to enforce going to states where your model is not well fitted, in fact. And so these are the exploration bonuses that are based on prediction errors, I call them. And the second class of intrinsic bonuses that you may add are entropy-based. So typically, so the most classical, I guess, is the entropy of the policy that you add to your objective function, which basically can be written as having a reward bonuses that is proportional to minus the log of the probability of the action in the current state. And there is also the same for the state occupancy measure. So you can also say, okay, what is the log of the probability to have a state that I have observed in this trajectory? And usually we don't look at the whole state, but at some feature of that state. And so this is the second type of intrinsic reward bonuses, which are called entropy-based, in opposition to the uncertainty-based, which were this first kind when you have a model and you want to penalize or to enforce the errors of between the model you have trained and between what you truly observe. And so I distinguish two terms, which is the return, expected return, and the intrinsic return, as I call it in the paper, which is basically due simply to the linearity of the expectation. And you see that it's basically the sum of the expectation of rewards function. So you may think of it as one is the true return and the other is the intrinsic return. So what you enforce with these exploration terms. And so the thing is, we now optimize the surrogate learning objective. But what we want is that the policy that we get when optimizing this surrogate objective function, assuming that it is possible and easy to optimize it, we want it to be close to the original optimal policy. basically, if you add some reward that completely enforce behaviors that are not optimal, what is going to happen at the end of the day is that you are going to converge towards a policy that is just of poor quality compared to the initial measure, which was the return of the policy. And so the first research question was about, is it possible to get conditions that link the learning objective function and the return, such that when we optimize the learning objective, we get some policy, or we would expect to get a policy that is of some good quality. And so the first thing that I'm going to look at, so maybe a side note, is that we optimize this learning objective with stochastic gradient ascent. And stochastic gradient ascent, so in general, if we forget that we are in an MDP and stuff like that, well, it's guaranteed to converge towards a local maximum under some condition. And if the function is pseudo-concave, well, we know the pseudo-concave is some generalization of concavity, which means that basically there is a single local maximum. Well, then we are guaranteed to converge toward this global maximum, which is the only point where the gradient is going to be 0. And so based on this intuition, we can derive a first condition, which I call the coherence criterion. And I say that a learning objective L is epsilon coherent if and only if the return of a policy maximizing the return minus the return of a policy maximizing the learning objective is less or equal to epsilon. So I optimize one policy maximizing the return, assuming that it's possible to do so. So I look at the best policy maximizing the return and the best policy maximizing the learning objective. And I look basically at the suboptimality gap between these two policies. And I say it's epsilon coherent if it's bounded by epsilon. And so basically, if epsilon is equal to 0, it means that maximizing the learning objective will provide you an optimal policy.
And the learning objective is the one with the return plus the intrinsic motivation, or which one is the learning objective?
Exactly.
Okay.
So here, this theta cross, let's call it like that, is the parameter that maximizes the return plus the intrinsic return.
Okay, I see. So this is a measure of comparing how good the optimal policy or the policy under theta star from the true return versus the policy from the return plus intrinsic motivation, so to say.
Exactly.
Okay.
And so it means that assuming that you can maximize the learning objective to the global maximum, well, if the coherence criterion is respected for a given epsilon, well, then you know that this policy is at most suboptimal by epsilon.
Okay, understood. And when you say epsilon coherent is just this, meaning that this epsilon is the difference between the two, right?
Exactly.
Why there is no absolute value or something like that? Like, couldn't this be negative? For example, j pi, what do you call that? Pi plus.
Pi theta star. No, because so you could say, okay, there is the absolute value, but this is always positive because the first j pi theta star is the maximum.
Okay, I understand. Yeah.
So it's evaluated in the argmax, so it's the max. And so when you subtract something, well, it's going to be positive, whatever. So you don't need to take an absolute value.
Yeah, understood.
And so the thing now, let us assume that we have this epsilon coherence. The question is, under what condition could we find this this p theta cross that maximizes the learning objective? Well, we can think again about the two conditions I gave for stochastic gradient descent to converge. And well, basically the function must be pseudo-concave. So it means that a learning objective must have a single global maximum. And so I say that the function is pseudo-concave if there exists a unique, so this exists with this weird exists there, is mean there exists a unique theta cross where the gradient is equal to 0, and at that point, well, it's equal to the maximum of the function L, so the learning objective that you maximize. And so if this criterion is respected, what you can expect is that stochastic gradient ascent is going to converge towards the global maximum of the learning objective. And so if this learning objective is furthermore epsilon coherent, well, then you can say that you are able to maximize, or you should be able to maximize the learning objective, and this maximum is going to provide you a good policy in terms of return. So if these two criteria make sense, I'll just show you a quick example. And so basically, we are going to consider...
sorry, Adrien. Yeah, sorry to interrupt you again. But, are you going to show later why the L that you consider, which is return plus intrinsic, is pseudo-concave?
I'm going to show you now that it is indeed the case.
Okay.
And the why, well, this I don't have the answer.
Oh, I see. Okay, no problem.
So here I say that if it is true, well, then it will work. And what I'm going to show you is that on a simple environment where we have nonlinear dynamics, well, adding the entropy may help. And then we can discuss a bit why it helps in this case and for what kind of system it's going to help. But I believe it's very complex to a priori say where it's going to help and where it's not going to help, in a very general case at least. And so this toy example is basically a kind of driving problem where you have a valley that looks like this, so like the blue curve, and you have a car that you want to bring to the target position, and you start at the initial position, x initial. And so the thing is that if you want to go to the target position, you have to accelerate to climb up this cliff and then to go back into the valley to the target position. And what I do is that I provide a reward to the agent that is proportional to its depth in the valley. And so basically, initially it has a reward that is going to be 1 because the depth is -1. Then when it climbs the valley, it's going to provide 0 reward. And finally, you get reward of 2 when you are close to the target. So it's proportional to minus the depth in the environment, in the hill. And for representation purpose, I'm going to consider a very simple policy, which is this policy here by GPK sigma, which says that I have a normal distribution over the actions, and the mean is k times the distance to the target position. And it has a constant covariance of sigma, or variance in this case. And so I have two parameters, k, which is the mean, if I may say, parameter, and sigma, which is the variance parameter. And what I consider are the two intrinsic rewards we saw at the beginning, which is the log of the probability of a feature of the state. And so here we consider the log of the probability to be at a certain position, so x in the valley. And we also consider a second intrinsic reward bonus, which is the probability, so minus the log of the probability of the action given the state. And so the learning objective is the expected over this policy and state distribution that it creates of the reward, so minus the depth in the policy, plus the weighting of these two intrinsic reward bonuses, namely the minus log visitation probability of the position and the log probability of the action provided with the state. And so what I'm going to show you here are 6 plots. And in each plot, I consider different values for the λ1 and λ2, so the weights of the intrinsic rewards. And I plot basically the heat map of the learning objective. So the darker, the higher the learning objective. And there are two additional information. This green area, which represent the area in which the learning objective is at most epsilon. So here epsilon is 1 smaller than the return. So basically, if you have a policy that is within this area, you know that you are suboptimal by at most 1 in terms of expected return. And the black dot is the global maximum of the learning objective, and the gray dot is, if any, the local optimum. So if I take the first picture here, the A, I've taken a weighting of 0.05 for the minus log probability of the state visitation. And what I see is that the learning objective has two local optimum, one close to 0 and one close to -1 for k, all having 0 standard deviation. And in addition, I see that the global maximum of the learning objective is within a range of 1. So this policy corresponds to a policy that is at most suboptimal by 1, so it's in the green area. So what I can conclude is that here I am epsilon coherent for epsilon equal to 1, because this global maximum is within the green area, but I'm not pseudo-concave because I see that I have two local maximum. So this learning objective respects the first criteria, but not the second. And if I look at the extreme most figure, so F, here I look at another combination of the weights. So I give a lot of weight to the intrinsic return corresponding to the probability of actions. And what I see is that here I have a single global maximum, but that corresponds to a policy with a high variance. And so it is epsilon, it's not epsilon coherent for epsilon equal to 1, but it is pseudo-concave. So we already see that there is some trade-off. So for some values of weights, lambda, I have one criteria that's respected, for some not. And so if I go back to A, B, and C figures, so these represent 3 weights. So I have put 0 for the probability of actions, but I have a value that is small and becomes larger, 0, 1, and 1, for the weighting of the probability of the state visitation. And what I see is that when I have a large weight, I lose the epsilon coherence, but I gain some pseudo-concavity. But if I have a good intermediate value, well, for B, you can see that you have a single global maximum for the learning objective, close to -1, and close enough, meaning that it is within the range for the epsilon coherence for epsilon equal to 1. And so when you add this exploration bonus based on the state visitation entropy, it is possible for a well-tuned value of lambda to get the two criteria that are respected. And so you may assume that it is going to be easy to optimize. But when you look at the other intrinsic reward bonus, so the probability of the action, which is basically the most standardly used exploration bonus. So we usually see in the algorithm that it's necessary to add the entropy of the action, which is going to be equal to the intrinsic return corresponding to this intrinsic reward. But you see here that it's impossible to get whatever the value of lambda you choose, both criteria that are respected at the same time. So it's possible for some case to have one of the two criteria, the other, and sometimes, depending on the intrinsic reward that you consider, it is possible to have both criteria that are respected or none. And so the first observation is that within this kind of simple environment, we can already illustrate that sometimes the criteria are respected and sometimes not, which may explain why these exploration reward bonuses work in these cases. Does that make sense? Because I know it's a lot of information and figures at once.
Yeah, I think it's clear.
So okay, maybe some intuition about why adding this exploration reward bonuses is going to be good. If I go back to a figure, so to the previous figure, this the probability to be in a state is going to be large when you have a policy that travels along the whole valley. And so for a large probability, I mean a spread distribution rather. So you're going to have a spread distribution when you have a policy that is going to be optimal. And so we kind of see that it is possible to maximize a bit, if I may say, the entropy of the state visitation and get an optimal policy. On the other hand, when you have a policy that does a bit of random, you have a low probability to reach this low point. And so this is the reason why the entropy bonus based on the state visitation is going to be good, and why the entropy bonus based on the action probability is not going to be good. And so we may think that the story is basically over. So when we have these two criteria, the learning objective is going to have good properties, and so we optimize it, and it's okay, it's working. But in fact, this, when we assume this is true, if we had access to the real gradient of the learning objective, but we don't, because we built stochastic approximations at the first hand, and also so in addition to building stochastic approximation, we built a very bad stochastic approximation because we have to neglect some partial derivative. So typically we neglect the influence of the dependence of theta in the reward, in the intrinsic reward, because I haven't written it explicitly, but the intrinsic reward now depends on theta because the probability, the state visitation probability depends on the policy, and obviously the probability of an action depends on the policy too, so it depends on the parameter theta, and this dependency is basically never captured when we do a policy gradient. So we are going to optimize these functions, so even this pretty looking function, but with a arguably poor stochastic approximation of the gradient. And so just to summarize a bit what we have done so far, so we've seen that there was some kind of trade-off between the two previous criteria. And one way to balance this trade-off may be to schedule the weights. So for those of you who have implemented the policy gradient, you know that sometimes it's interesting to discount the entropy penalization. And maybe the most interesting point is that when we interpret entropy bonuses like this, well, it's absolutely not the same role as in value-based RL. So in value-based RL, you know that it's exploration, but because you have to keep your policy sufficiently stochastic, here is not really a question of stochasticity, but it's more a question of learning objective. And indeed, the smoothing effect of entropy regularization, so policy entropy regularization, has been long known, or known, I don't know, but recent work have studied this very well, at least depending on how it modifies the optimization procedure. And in particular, there are several works that show that it is linked to robust optimization. And so the story is not over, as I said, because even pseudo-concave and coherent learning objective function can be, in fact, very hard to optimize. And this is due to the fact that we use stochastic approximation of the gradients. And here, what we want to look at is if we can build, once again, some condition such that we expect the stochastic gradient ascent to be fast enough when we optimize it. And by fast enough, so I'm going to define it, I'm going to say that it's going to be fast enough if it has a high priority to improve the learning objective. So if one stochastic gradient ascent step has a high priority to improve the learning objective. And so once again, I start with a quick reminder of optimization. So the improvement of the learning objective when we perform an ascent step in the update direction hat D is provided by this random variable x, which is equal to the difference of f theta plus the update in that step plus alpha at d minus f of theta. And so this alpha is the learning rate. And this to the first order is equal to alpha times the scalar product between the update direction, so the stochastic gradient estimate, and the true gradient of the function f. And so in practice, when we look at asymptotic convergence, what is common is to compute the expectation or try to bound the expectation of this random variable. And then we know that one ascent step will on expectation update by that value, so this bounds at most, and then we can get convergence guarantees. But this is very complex to do, and so what I'm going to do is to look at the probability that this random variable is positive, meaning the probability that we have a policy improvement, so that one step of updating the policy in that direction is going to improve the policy. And so there are two ways of interpreting that. The first is to say, okay, in fact, the convergence is going to, so each ascent step is going to improve by a constant value the function, be it positive or negative. And so for having a large convergence guarantee, we must have a large probability of improvement. Or the second way of seeing it is to say, okay, what I don't want is that the asymptotic convergence is driven by events that have a low probability. So you know that, so that's exactly what is happening when you have sparse reward environment. On expectation, you have a positive gradient, but in fact, this expectation is positive simply due to the fact that you have the probability over the probability of the lucky event of a correct update is small, but it has a high value, and so an expectation is positive, it's high. And so we look at the probability that this random variable is positive, so the probability that we improve the function f. And here the function f is going to be the learning objective. And so the remaining slides is about computing or illustrating criteria on the probability that a gradient ascent step is going to improve the learning objective or improve the return. It's maybe easier if we directly dive into the criterion. So I say that an exploration strategy is delta efficient if and only if the probability that a gradient ascent step in the direction hat d improves the learning objective, and that this probability is greater than delta. And so this, I say it like that. For almost all theta, the probability of random variable d positive is larger than delta. And this d random variable is the scalar product between the direction in which we perform a step and the true gradient of the learning objective. And so if this is large, it means that very often when we perform an ascent using direction d on the learning objective, is going to improve the learning objective. Typically, if d is equal to 1, it means that each stochastic gradient ascent step improves the learning objective.
Adrien, sorry, can you go back one slide, please?
Yes.
So can you explain again, please, about what is d hat in your case? Like in our setup of RL, what would this d hat be? Because I thought that would be the gradient of
It is not the gradient; it's the stochastic estimation of this gradient.
I see.
Okay. Reinforced. Typically, it's the reinforced estimate if we perform.
Okay, and your definition in the second slide is just saying that if my estimation is correlated or if it has an angle correlated with the true gradient, right? Mm-hmm. Then I will get an efficient exploration strategy, right?
Exactly. And by efficient, it means that stepping in that direction will improve the learning objective with high probability.
Yeah.
And so you know that there is noise on this hat D, so this reinforced estimate, and that in practice, sometimes you perform several updates in the good direction and several in the bad direction due to that noise, to that distribution over reinforced estimate, or in a general case, ascent estimate.
I see. So in other words, this gradient theta is like assuming you can compute the oracle expectation.
Yes.
And d hat is just like a Monte Carlo sample or Monte Carlo estimate.
Yes, exactly.
Following on policy, I guess, right?
Mm-hmm.
Yeah.
Yes,
okay.
yes, everything is on policy.
Okay, yeah. Okay, got you. Okay.
And so we can expect, if this delta is large, that the Monte Carlo gradient ascent is going to be very fast, because we will very often improve the learning objective. So here in practice, you may not look at d greater than 0, but greater than some threshold, in order to avoid that you have reached some plateau, for example.
Yeah. Okay.
And so
okay.
this is interesting, but there is a last criterion that is probably much less intuitive, which is the following. And so I may be going to first introduce the intuition, and then to look at this criterion. And so the intuition is that in practice, it is very easy to compute good estimate of this intrinsic return. So it is very easy to have estimate of the intrinsic return that provides you with a good direction. And on the other hand, it may be very difficult to compute estimates that will improve the return. And so if you perform stochastic gradient ascent, in that case, what you may have at the end of the day is that you converge towards the global maximum of the intrinsic return and not of the policy, of the return of the policy, because you will see that there is no improvement of the policy, because this efficiency for the policy in some sense is going to be low. But on the other hand, since it is easy to optimize the intrinsic return, well, you still see an improvement of the learning objective, but simply because you are improving one of the two terms. And what you want is that when you perform this optimization, well, you want at some point to start optimizing also the return. And so what you may say, the first idea is to say, okay, what I want is some equivalent of the efficiency criterion that would say that, okay, at some point, the update hat D is going to provide me a high priority to improve the return, in addition to improving the intrinsic return and the learning objective. But this is, again, a bit naive, because you don't want this to be high everywhere. What you want is that once you have reached the global maximum with high priority in some sense of the intrinsic return, then you want the priority of improving the return to be sufficiently high. And so by this, I mean that we want for a ball that is centered in the global maximum of the learning objective, and that contains the maximum of the intrinsic return. We want in this region of the parameter space that the probability of improving the return following this ascent step at D is sufficiently large. So all of this barbarian notation is basically telling you that in some region of the space, if I follow the ascent direction at D, so the reinforced and the learning objective, well, I also improve with probability delta the return of the policy. And this region of the space is not randomly chosen, but is the one that first contains the true maximum of the learning objective, and also the maximum of the intrinsic return, which is the point towards which you are subject to converge if you have a low probability to improve the return everywhere else.
Right. So could you remind us of what was theta plus theta dagger? What was that?
Yes. So theta dagger is the argmax of the learning objective of L theta.
Right. So you're saying, okay, you take the learning, you take theta dagger, right? Then you define a ball around it, right? This is B. And theta dagger is the return plus the intrinsic part, right? So that's the return plus the intrinsic part. That's what it optimizes, right?
Yes.
Right. And now, just consider that theta intrinsic is within that ball, right? And then you're going to say that the attraction criteria is that if I start from there, I will actually get attracted to maximizing the true return objective.
Exactly.
So it's like a stability criterion in a way, no?
Yes.
It's
so
like a level of yeah, okay.
So it was basically the intuition between this attraction name is that stochastic gradient estimates are going, to provide you trajectories that are attracted towards some kind of stable point with high probability, which is the global maximum.
Yes.
And so this is somehow, so the first criteria was the equivalent. So for the whole state space, you want trajectories to be attracted to the global maximum of gradient of L max, in fact, sorry.
Okay. And one last question, so maybe it's a naive question, but why is theta intrinsic belonging to the ball around theta dagger? Or is it because I can grow the ball radius as much as I want, really?
No, so this ball, so why should theta int be within this ball is the intuition that I said that as it is easy to compute gradient estimate that will improve the intrinsic return, you are likely to converge towards that point or to be attracted to that point when the efficiency criterion is respected.
Okay.
So it's not really a guarantee, but intuitively, efficiency criterion say, okay, you are likely to go towards the intrinsic max or towards the global max, but you want to be attracted toward the global max, and so you have to guarantee this attraction in addition.
Thanks.
And so this may sound a bit like two criteria that falls a bit out of nowhere, but I'm going to illustrate on a simple example again that in fact these two criteria are respected when you work on a simple environment. And so this simple environment is a maze environment, but that is simplified to a point that basically it's simply a horizontal corridor where you start at left and you want to reach the point at the highest tile. And so there are S tile, and you have two actions, left or right, and then you move in the corridor like that. And so you have a probability to stay idle when you perform an action. And so basically you have to be optimal to perform always action I want to go to right, and then you will reach as fast as possible the target position where you have a positive reward while it is zero everywhere else. And so the thing is that you already see it, that if your policy have a low probability to go to the right, you will never observe a positive reward. And so the policy that we consider here is a very simple one. It is one parameter, theta, that gives you the proportion of actions that are going to the right. And so if theta is equal to 1, you are going with probability 1 to the right. And then, you are going to go as fast through the horizontal corridor. And so, again, I consider the two intrinsic return that we previously discussed, so which is going to be the visitation probability to be in a state, so in one tile, and the probability of the action that's provided by the previous policy. And so here I represent in black in figure A the return of this policy. You see indeed that for small values of theta, you have 0 values. So you don't observe, it's basically not 0, but you observe a very, very small return. And when the probability is high, well, you observe a high return that accumulates when you reach the terminal state. And I also represent the entropy, basically, so the expected log probability, so this intrinsic return, in red for the probability of actions. So it is the entropy of the policy, basically. It's going to be maximum in 0.5, so a uniform policy, and minimum for policies that go always to the left or always to the right because they are deterministic. It's a bit more complex when you look at the probability to be in a certain state. So it's going to be maximized around 0.7. and it increases a bit from 0 to 0.7, and then it decreases again. And so this is a weird effect of the gamma that is going to weight this distribution. And then if I sum both intrinsic return, both the intrinsic return and the return, I get the learning objective in the right figure. So in black again, the return of the policy. In red, the return plus entropy of the actions, and in blue, the return plus the entropy of the state visitation measure. And what you see is that the three functions are pseudo-concave. So basically, if you have the true gradient, you can always go in the right direction. And they all have their global maximum and unique maximum too in theta equal to 1. So basically, with respect to the two previous criteria, there is no reason to prefer the one or the other learning objective, because they all respect epsilon coherence for epsilon equals 0, and they are all pseudo-concave. And so what I'm now going to look at is to look at the probability of improvement. And so here it's a very simple environment. So the probability of improvement is simply the probability that the derivative of the learning objective is positive. Derivative, so it's no longer a gradient because there is a single parameter. And so this is this figure. And so in black, I have the probability that the reinforced gradient, so Monte Carlo gradient of the return is positive. In red, the Monte Carlo estimate is taken for the learning objective with the entropy of the policy, and in blue, the learning objective takes into account the entropy of the state. And so there are two things that are interesting to observe. First is that indeed, when you look at the reinforced estimates of the return for small parameter theta, it has a probability of improvement that is 0. So if you start with a probability that is a low probability to go to the right, you may optimize as long as you want. You will never reach the optimal policy because you're in a sparse environment. You never see the reward, and so it doesn't work. On the other hand, when you look at the learning objective taking into account the entropy of the policy, so the red, what you see is that when you have an entropy that is a parameter that goes often to the left, so a small parameter theta, the probability of improvement is equal to 1. And this can be understood because basically the return has no influence on the learning objective, because the probability of improving it is going to be 0, whatever. And so what you compute when you perform reinforced updates is to compute the estimate of the gradient of the entropy, which is very easy to compute and provides you a direction that leads to increasing the parameter theta going towards 0.5, the maximum, which also happens to be a direction in which you increase the return. And so for that region of the space, for 0 up to around 0.4, well, you are efficient with delta equal to 1 because you perform policy improvement at every step. And what is interesting is that when you come around the global maximum of the entropy of the policy, well, you have a sudden drop of the efficiency, so meaning that you have a much lower probability of improving the return. And why is that? It's because basically the reinforced estimate of the intrinsic return, so the entropy, provides you a gradient that goes backward. So if you want to maximize the entropy, you have to reduce theta. So basically, there is no longer this collaboration between maximizing the return and maximizing the entropy. And so here, the second criteria comes into account because we are typically in the region where we have a ball. So here it's an interval that contains the global maximum, so theta equal to 1, and the maximum of the intrinsic return, so theta equal 0.5. And you can say that in that interval, well, we are lucky enough to have an efficiency that is about 0.2. And so it means that there is still some probability that you improve the return. And what you see is that the farther away you go from the the global maximum of the entropy of the policy, while the higher the probability of improving the return. And this simply comes from the fact that you see so many times the target position when we have a theta that is close to 1, that is going to dominate with high probability in some sense the estimate of the gradient of the entropy of the policy. And so here we can see the interaction of the two criteria that are needed if you want to have a good convergence. And interestingly, if you look at the entropy of the state visitation, well, it is almost always large, but it's never equal to 1. So what it means is that first, as it is always large, it can be assumed to be a good exploration bonus, considering that you want to have high probability of improvement. But yet you never reach this 1, and this is likely due to the fact that in order to estimate this distribution, you have to use a more complex model. So you have to build a model over the state distribution, which here is done using some what do you call it? A histogram, sorry. And so the histogram comes with an approximation. And so this approximation makes it such that sometimes you don't perform improvement. And so here, interestingly, is that the second criteria is not really necessary. So you see that indeed you are still sufficiently efficient. You don't have this drop of efficiency when you reach the global maximum of the intrinsic return, which is likely due to the fact that at this point you already see very often the target position. So you have a parameter theta that is sufficiently large such that what dominates in this interval is the influence of the return, and the intrinsic return is somehow less influent, dominates less the learning objective. And so interestingly, so this is the conclusion slide, we have seen that exploration has two effects, one on the learning objective on expectation, and one on the estimate of the gradient and how it is going to influence the optimization. But probably the most important is to remember that these exploration terms are only proxies. So to have a good learning objective, it's not basically you can have anything else. It does need to be really exploration based in some sense. You can simply do reward shaping if it's possible and use the same criteria, because it's simply these are proxies that appear to have good properties, but it's not the objective is not to explore, it's just to have a good learning objective. And well, interestingly, for the simple example that I've presented, entropy bonus have good smoothing properties. And if you go looking in the article, we performed extended experiments on more complex environments, and we see that again, entropy bonus, in particular the state visitation entropy, is pretty good for guaranteeing that the 4 criteria works. And I'm convinced that exploration is not that well understood. In particular, well, usually we don't distinguish between the two effects. I've never seen a paper that we say, okay, here we deal with sparse environment, so we look at the estimates, and here we look at environment with complex dynamics, so we look at the return function. This I've never seen, so I believe that there is a need to, if I may do the joke, to explore in that direction. And I truly think that there are steps to go to get with formal proof. So now I've introduced 4 criteria, but in fact there is no real theoretical guarantee behind that. It's more based on the intuition and observation. And I think that building upon that could help alleviate some common folklore, as I like to call it in the literature. So if there are questions, feel free to ask.
Thank you. Thank you so much, Adrien. Yeah, this was very interesting, actually. So your work is more, let's say, on the analysis fundamental level, right? Trying to fundamentally understand what is going on, when we do these exploration bonuses inside RL, which I think is pretty amazing, and we need to do more of that research. So well done. I think this is awesome.
Thank you.
So I just want to ask you a question in general. Um, so this has been, let's say, an analysis paper, maybe, right? Like trying to do some definitions and trying to look for them in experiments, right?
Mhm.
Um, do you think in the future this could be transformed into a design paper where we actually, when we are optimizing in RL, we actually do constraints like the ones you mentioned in order to have a better exploring policies?
Well, yes, I think what will be so the criteria as such are basically not possible to use in practice, right? Because you have to get this oracle of the gradient or of the learning objective, which you don't. But what would be nice is to say, okay, if I use this exploration term, and maybe with this schedule on the parameter lambda, that then you have some guarantee that at some point the criteria are respected. And so this could be, but I guess that is going to be very dependent on the environment,
Right.
because you can assume that for some environments, having a stochastic policy is a bad idea, while you may typically, if you initialize directly your policy on the optimal value, well, all this exploration is going to be unnecessary, and it may drive you away from the solution. So
Okay.
this would be
Okay.
nice to have an exploration that guarantees the criteria, but to do.
Do you? All right, I see. Got it. And do you plan to have a broader set of experiments, like beyond these setups you considered? Because I understand this is fundamental work, so it needs, to start somewhere. But do you believe in the future you want to try this on deep RL settings, for example, with, I don't know, like complex domain or something like that?
So one limitation is that you have to select your environment such that, well, you can somehow look at these criteria. And so if the environment is too complex, well, you lose everything. And what I've been doing in the appendix of the paper is I took a policy that was a neural network of several hidden layers.
Hmm.
And what I look is that I optimize the policy, I get a trajectory of parameters, and I look at the criteria over this trajectory. And so basically over the parameters so basically over a trajectory in the parameter space, I can somehow analyze the criteria and look at, okay, is the probability of improvement sufficiently large for this trajectory and stuff like that. And so this I've already done, a bit generalizing towards deep RL, but still the environment was sufficiently simple such that I could basically get rid of some problem that arise due to the optimization. For example, you need a model of the state visitation distribution, which in practice is absolutely not trivial to get.
Right, I see. Okay. Yeah, and one last question from me. So I do see that you've been trying to understand RL, in this perspective. But do you believe we could use your technique to actually design better optimization algorithms? Um, because I saw this like two local minima function you considered, right? So
Mm-hmm.
so that's interesting because you kind of are designing a method which allows you to avoid this bad local minimum and go to the better local minimum, right? Do you think criteria like this would actually be useful in analyzing like non-convex optimization problems in general?
Yes, I believe that maybe it will not help to build new optimization algorithm, but provided with one optimization algorithm, I think that the analysis generalizes to any problem. So many problems, I would rather say, where you optimize a surrogate learning objective. So typically a lower bound or an upper bound if you maximize or minimize of your true objective function, or if you have a stochastic estimate of the gradient, which is usually the case in machine learning. So
I see.
yes, and interestingly, for example, the criteria do not use
Hmm.
the assumption that we have a sum of return. So basically, you
Yeah.
can use it for any surrogate in
Yeah.
RL already. And so we don't really use neither the fact that the return has some structure. So it's likely to generalize to some extent to other stochastic optimization problems with a surrogate learning objective. Yes.
Very interesting. Yeah. Yeah, that would be cool actually. Nice. Yeah. So Philippos, Alex, Mathieu, do you have any questions?
Hey, Adrien. Yeah, I do have some questions. Thank you for the talk.
Thank you.
That's very interesting. I was wondering how did you model the state visitation? So I understand that in the last experiment it's a histogram, and
So in both experiments, it's in histogram, because in the first, we only look at the position, so it's unidimensional. And in the second experiment, we look at the tile, so it's also unidimensional. And so in both cases, I used an histogram that was built by extensive sampling. So I sample a lot of trajectories to get the histogram, and then I can estimate the rest. And in the extended experiment I did, I used the Gaussian mixture models. And in practice, you can have a neural network that you optimize in parallel to your policy to fit this distribution. Did it answer a bit the question?
but in the case of the neural network, what would be the objective?
You mean for the learning the state visitation?
Yeah.
Well, what I did was naive. So I simply looked at the trajectories that were sampled for building the gradient estimate, and I fitted a Gaussian mixture on that using scalar. So probably the most trivial thing you can do. But if you want to have something that is a bit more intelligent, you can look at the gamma models. It's called like that, I believe, that were developed by Sergey Levine's team. So they have a neural network, and they do basically some kind of Monte Carlo estimate with a bootstrap to learn this distribution with another neural network. That takes as input the state and provides you the likelihood.
I see, thank you. And just to be sure, in the one slide before this one, in the clocks,
yes,
you add here you add the two criterion with a weight of 1, right, for the exploration.
Yes. So basically, it's a weight. It's not a weight of 1, but here. So this is the entropy weighted by, I believe, 0.1, but it's simply the sum of the return and the intrinsic return, which are both represented on the figure. But if you look at the definition here, the intrinsic return already, where was it? Here, the intrinsic return captures the weight. So what I plot is the intrinsic return, so weight accounted.
Yeah, okay. I see. And you mentioned also that the maximum of your J criterion is always positive. I don't understand why. I'm missing the process.
So come again, the maximum of
your J criterion.
So the maximum of your J criterion. Oops. So here.
No, it was before. It was a question we can answer.
Yeah, so if you go back to where you defined this epsilon, what did you call it?
This?
Coherence. Yeah, so I think Matthew is trying to understand why J pi is always positive, right?
It's not always positive, but the difference. Well, because you this is the maximum of the function minus something else, so it can only be.
Yeah. Okay, positive. I get you. Yeah, okay. Okay, thank you very much. That's all on my side.
Thank you for the questions.
Yeah, thank you, Mathieu. Yeah. Any other questions? If not, I will have one more. But let's see. Alex, Philippos, any questions on your side?
No, thank you, but nice talk. Thank you.
Thank you.
All right, cool. Okay. Right. So one last question, maybe not so related to the specific talk here, but we're asking everybody who's giving us a talk to tell us more about how their interview process has been going, right? Because we know that how the review process, has been going. So we know that a lot of people are complaining about the review in the machine learning community. And what has been your experience with that? And maybe if you have any ideas to improve, that would also be good. So maybe you can say a word or two on how your experience was.
Interesting question. So This paper was rejected at iClear, so you can see the review online. So go ahead, and what you will see is that it was a typical problem where there were not enough experiments, and so fair enough at some point, because indeed we were lacking some interesting experiment that we did, and I believe that now we have enough evidence. But the question is always, since I'm in a problem, as I told you, that I have to keep the experiment under control to be able to show things, that I hope I won't get the same remarks if resubmitted, and we'll see. But indeed, I think that there is it's always complex when you do papers that are a bit in between something that is very experimental and something that is very theoretical, because it's a bit none of both worlds, and sometimes you get hard reviews.
Yeah, no,
and
I
how
understand.
to improve that? Well, it's a good question. I'm a naive PhD student, so I'm not sure I can give something very deep about that.
Okay. Well, that's a very political answer, I see. No, okay, yeah, that makes sense. However, I would definitely urge reviewers to consider papers like this more importantly, because they're really important analysis papers, and I think there isn't enough of them, right? There's more like, I have this new algorithm, look at my method, but rather than why things work. I think this is important. So yeah, that's a good point, and yeah, it's hard to get these papers accepted. However, yeah, I'm sure you'll get it in. It's actually awesome analysis paper, I think. Yeah.
Thank you. And I agree.
Awesome. So, Adrien, I want to thank you again for coming and talking to us in this episode. This was really, really exciting. Send my sincerest greetings to Damien. And I know this is Damien's style, so I'm sure he likes what you're looking into. So, so thank you again, and yeah, thanks everybody for joining us. This has been our current episode of Mete with the Researcher, and I will see you next time. So thank you, Damien, again.